All right, welcome everyone for the next session. So we have a Weaponizing MCP Servers production ready AI agent infrastructure with Python by Kushal Vijay. Can we all welcome Kushal Vijay, please, with a round of applause.
Hi everyone, thank you for coming. Today we'll be diving deep into MCP servers, how we can build those, how to make them sustainable in production. So everything works in demos, everything works in your local machine, but when it comes to production, things tend to fail. And that's the bridge we are going to fill today. Like, we'll be talking about a lot of patterns that need to be followed when it comes to building MCP servers in production for the production infrastructure. So how many of you have ever built a MCP server or tried building it? Has anyone? Oh, that's great. How many of you have built an MCP server which is running in production today? Okay, so looking at the number of hands getting down to 0, this says it all, that building an MCP server which survives in production comes with a lot of intricacies. Because in production, external APIs fail, we have database failures, we have network hiccups, and so on and so forth. And we'll see how we can fix those by understanding the problems first, and then what are the solutions for the same. Now, for any MCP server, the foundation starts with the async patterns. All the MCP server follow, the foundation is the async operations that we use to call different APIs in our servers. Now, the common tutorial or the common mistake that everyone do is they create a HTTP client, as you can see here, and they make a HTTP connection, and then they keep it open. That's the most common tutorial you'll find on the internet. Everybody uses that for their demos. It works pretty well in the demos, but when it comes to production, it acts like a slow poison. With every request in local demos, you might have a few requests to handle, but when it comes to production, it acts like a slow poison. When you'll have one request, it works fine. When you'll have 100 requests, you will have 100 open connections. And when you'll have 1,000 requests, your server tends to die. And the code is pretty simple. The code is pretty innocent, and you'll find it all across the internet as a tutorial, and everybody follows that, makes the same mistake again and again. The problem here is the connection leaks. If you see here, what we are doing apparently is we are making, so I've stimulated the whole process of this connection leak, where I'm making 20 requests here, and all of them are creating an open HTTP connection. And with time, you'll see, so when I ran this simulation, what I have seen is with every request, you tend to have a lot of memory consumption, there'll be a lot of latency, and eventually, when this is good for work like local demos, but you cannot put this into production, because if you see the growth of memory consumption, the latency with time, or with the request, the server will tend to die at the end. So post the 20th request, we have like 20 sessions which are open, which were never closed. There are more than, per request, per session, we had like more than 10 to 50 connections, and which led to 1,000 open connections by the end of this whole simulation. So you see the growth of memory with each request is growing exponentially. Now, how to fix this? We use connection pooling. That's the survival. The fix is connection pooling. Instead of creating new connections every time, we tend to set a connection pool, which will be used as per the availability for every request that is incoming. It's like carpooling. Instead of using your own car every time to go to the office, you go with your friends. You save time, you save fuel. So how does it work? Here again, we are making 20 requests. I'm simulating 20 requests here, but here I have a TCP connector with a transfer control protocol connection, which has set to 20, which makes a connection pool of 20, and every time you make a request, it uses an available connection pool from the TCP connector pool that we have initially created. The async width here takes care of doing all the thing on its own. It'll fetch one of the available connection pool. It also is a context manager which automatically handles the cleanup part, and the session which will automatically pick the available connection pool, and once the request process is completed, the pool will be available again. So the async pattern problem can be solved with this connection pool survival pattern. Now, the performance results were insane. If you look at it, it took the 20 requests with the connection pooling takes 2.18 seconds, which is fairly better than the initial async pattern that we followed, which took more than 10 seconds. Average time taken by each of the requests was 100 milliseconds, and they were concurrently executed. All the requests were taken care in parallel. Now, this is fine, but when it comes to, once you have set up the connection, there could be hundreds of AI agents requesting through the same connection. And that will create a lot of chaos. All will hit the servers at once. The server will overwhelm, and then that leads to complete failure. Here comes the traffic controller, which is rate limiting. Without rate limiting, the server tries to execute everything at once, and which leads to a lot of resource consumption, and the server overwhelming, which eventually lead to the dying of the server or killing the server. It's more like going to a restaurant during the rush hour which has no reservations. You tend to give seats to everyone during the rush hour, and your chefs tend to fail, or the services tend to fail. Now, rate limiting, in this particular pattern, I have demoed two things. One is with rate limiting, and one is without rate limiting. What are the benefits we get out of it? So first, the chaos part, where we execute multiple requests, maybe 10 tasks without any rate limiting. So everything executes at once, and the chaos time taken was around 1 second, which is faster, pretty cool. But there are potential problems with it. We don't have any control. It is not predictable, and it can lead to crashes in the external APIs. It can exhaust the resources that you have, the databases, and also it can hit the OS limits. So if you see here, we have 10 connections starting immediately altogether, and the chaos time taken was just 1 second. But what happens when we introduce rate limiting? We create a semaphore pool of 10 here, or we can create a semaphore pool basically to limit the number of requests going ahead. Or it's more like you're in a club and the bouncer is only allowing certain number of people into the club so that there'll be less chaos and things are in control. Okay, so with rate limiting, only 5. So if in the demo which I have created, I've taken a semaphore pool of 5. So only 5 tasks are executed at a time. It will be a batch execution. Once the 5 tasks gets completed, the next 5 will be taken into consideration. And the control time, basically since with rate limiting, we have the control. It took 2 seconds, but it is slower, but it is controllable, it is predictable. The key benefits which comes with this is resource protection. Obviously, it prevents overwhelming of our databases, operating system, and also reduces the network latency. The performance is predictable. Now you know the maximum load that can hit your servers, so you can prepare well before even while building itself. Graceful degradation, system stays responsive all the time because you know the maximum load it can handle and which can come to the server at once. Cascading failures. So when external APIs fail. So right now, till now, we were only talking about the implicit failures or implicit failures which can come from our side. But what if the failures come from the external APIs that we're consuming in our servers? That can lead to cascading failures. And when it comes to cascading failures, server keeps trying, our server will keep on trying, okay, give me some response, but there'll be nothing because the service has already died. For instance, let's take an example of the weather application or the weather API. The service is down, and your server is keep on trying to get the results, but nothing will happen because the service is dead already. And this is called cascading failure when the external API failures migrates to your server because you keep on trying and you're not getting any results. It can lead to a lot of timeouts. It can lead to timeouts and failures. Now, how to solve this? Circuit breaker, just like we have at our homes for electricity, we have close connection where everything works smoothly. We open the connection when we see that there are failures. There are a lot of failures that are happening in our MCP server, and we reconnect to our server again by half-open mechanism. We'll test it again in between to check if the service is up again or not. So how it works is we have a normal connection which is monitoring the failures. Every request that is coming, if it encounters a failure, we keep a count of it. And as soon as we reach a threshold, we make the connection open. And when the connection open, we tend to fail fast. We'll return early for whatever the upcoming request coming to our servers. This helps, and all the requests fail immediately, so we don't really hammer the dead service, which is the weather API in our example. Half open is a scenario where after a certain point of time, we make another request, a recovery request, to check whether the service is up again or not. We try to connect to the weather API, whether it is up again. If it is, we just make one request, and if it is up again, we make the system closed again and let the operations flow through the MCP server. If it fails back, we open the we make the circuit breaker open again, and it will not allow any more requests to flow through, and we fail fast. Now, the result of the demo that circuit breaker I have created before was, so initially the circuit was closed, but we encountered a failure, then we had 2 successful requests. Post that, we encountered another failure, then a successful request. But when we encountered the 3rd failure, we made the system open, which didn't let any more requests to flow through. And this basically helps in resource production. We stopped wasting time on a clearly failing service. Now, finally, which everybody loves scaling, right? So how many of you like horizontal scaling? How many of you like vertical scaling? If I'll say vertical scaling, anybody? Horizontal scaling. Yeah, everybody loves horizontal scaling. We'll be talking more about it. So generally, when do we scale? When we see that response times, depending upon your use case, is increasing quite a lot. When it comes to internal services, latency is not a big problem, but when it comes to customer-facing experiences, latency plays a major role. And when the response times becomes higher, is a very determining factor when we should scale. Memory consumption is climbing steadily, agents timing out, and then CPU consumption is also constant over the period of time. That too, like nearly 90% is when we think about scaling. Now, vertical scaling comes with its own pros and cons. You don't have to buy another machine. You can just add more computation. You don't have to make any code changes. But with horizontal scaling, it is infinitely scalable, but it comes with a lot of complexity and load balancing. Hence, we'll be talking about load balancing. It is one of the most important patterns that that needs to be taken care when we are dealing with MCP server in production. In load balancing, we have, like, for instance, we have 3 servers here, A, B, and C. We have to use an algorithm to assign server every time. Here we are using round-robin algorithm as you can see here, to assign server for any incoming request. And the results, if you see, when a single server execute all the requests, it can handle all the requests, but there is a potential single source of failure. There is a chance that it will overload. There is a high chance of failure because there will be maximum concurrent load and it will get overwhelmed. But when we load balance things, you see server A, B, C have evenly distributed request, and load is distributed evenly, which makes the server more reliant. It tend to perform better. It helps in better resource utilization and so on and so forth. Now, all these things, all the patterns that we discuss aren't useful if we can't see what's happening, right? So monitoring is one of the most important things which comes into play even before like pushing everything to production. Production problems are often subtle. Monitoring catches everything before even having the disaster in place. I haven't added the complete code because it's pretty simple. The monitoring doesn't have to be pretty complex to be effective. You can simply do logging using Python logging libraries, and if it's for like bigger purpose, then you can use Prometheus with Grafana for dashboards for all the monitoring part. But what are the essential matrices that we track when it comes to monitoring? Requests that are going per second, basically the throughput. Is the demand growing or not? Then the response times, the user experiences, how is the latency going on? What are the error rates? What is the memory consumption? Is the resource health fine or not? Are there any leakages? Connection health, the pool utilization, are we maxing out or not? With that, the logging part is pretty simple. You can use, and if it's for a bigger purpose, more customers, and tools like Prometheus with Grafana for dashboard is a good alternative. In short, the 3 laws for production MCPs is pool the connections, fail fast, fail safe, and monitor everything. And this will lead to, these are the best practices, or these are the patterns that one can follow. You can use all the simulations that I talked about in my GitHub. I'll share my GitHub, or you'll find my GitHub on my LinkedIn also. I'll share all the code snippets and the output of the performances there itself. Thank you. Anybody has any questions, please feel free to ask.
Yeah, questions?
Hi. I faced exactly this problem last year when I wrote a proxy server that would really cause some issues under load, like bringing down the entire company network. They won't let me forget that. But one thing that I found was a little bit arbitrary and difficult to answer was, how do you decide what is a reasonable number of connections? So for instance, you were showing a slide there where the server is crashing after 20 connections, and so then you redistributed it so you had 6 or 7 per server on 3 servers. But that's a very arbitrary number, and the answer to how many you should use, it's like how long is a piece of string? And I never really figured out how to answer that question in the end. So what would be your, not what's the answer to that question, because there isn't an answer, what would be your way of approaching coming up with some figures?
Yeah. That's a very good question actually, and since it was a simulation, I took 20 just to show to the audience, and it depends a lot on the use case that the company is handling. So one of the matrices that can be used for tracking is the scale of the audience that your server is handling right now, and the second is how many whatever the services your servers are using externally, the failure rate of those services are the 2 things that you should consider deciding the TCP connector pool size.
Yeah, exactly. So let's say those servers you're calling, they start to return 429,
Yeah.
which means I'm too busy, come back later.
Yeah.
Do you ease back as soon as you get the first 429, or do you keep trying? It's hard to know.
Okay. Yeah. So see, it's something that cannot be judged. This particular decision can only be taken over time. Like you monitor the data, how many times you're getting this 429, or is it like ad hoc failure that you're getting from a particular service, or it's more like it's a continuous pattern that you have been observing for a long period of time, and then you decide, okay, we need to increase our TCP connections pool. So I would rather say it's more of an analysis for a short duration of time, and it's more like the strategy that can be followed here is A/B testing. You go ahead with like 20 connection pool for maybe one deployment, and 30 connection pool with the deployment, and figure out what's working better, where you have lesser chances of failure, and that's how you can move forward with. That would be my stance. I know there is no perfect answer to this, but yeah, that would be my stance.
Thanks.
Anyone else? Any questions?
I think someone has raised from this side. You.
Hello, thank you for your presentation. I just have one question regarding how did you learn to all of this? Do you have any reference for best practices on MCP servers, especially when releasing to production? Thank you.
Yeah. Thank you for asking that. So I've been building and trying to build AI agents for a while now, and then while doing so, I follow these YC Combinator, podcasts, and there I found out that this MCP is going to be the next big thing. And with that, I got an idea of building. So I work in authentication area at Microsoft. So I got an idea to build OAuth for MCP servers. And with that, I got to know about ScaleKit, which is doing this work already. While learning about ScaleKit, things that they are following, I got to know about these things, and hence I prepared the talk around it.
Oh, I see. I see.
So that's the whole story.
Any other questions? No? Okay. I think, that's all. Thanks again for the wonderful talk, Kushal.
Thank you.
Again, can we all give a round of applause to Kushal?